to calculate the pH at equivalence of a titration. In this case, we have a weak acid titrated with a strong base. So if we are exactly at equilibrium, after our weak acid has been neutralized by our strong base, so in this case that would be hydroxide, what is going to be the product of that? Well, the product of that is going to be the bicarbonate ion or hydrogen carbonate ion, HCO3 minus AQ, and that in itself is basic. And then just we have the water. So we're looking at this reaction of our hydrogen carbonate ion with water, because that in and of itself is going to undergo hydrolysis, and that is what's going to drive our pH after the equivalence point for a weak acid titrated with a strong base to actually be slightly basic from the hydrolysis reaction of our weak base with water, because that is then going to go on with water to produce the weak acid that it's the conjugate of, and hydroxide. So essentially what we're going to have to do is work out what the concentration of this hydroxide ion at equilibrium is. So that is going to require an ice table, but we have to know what numbers to feed into our ice table to begin with. So that is where a little quick calculation is going to come in. So what we are going to need to do is we're going to first of all have to work out how many moles of our carbonic acid we have, so we know how many moles of hydroxide it's going to take to neutralize it, and therefore how many moles of the bicarbonate ion, HCO3 minus, we have, and then we can work out the initial concentration of that before the hydrolysis. And what we have to remember is do moles divided by volume, but it has to be that final volume from our carbonic acid solution with whatever hydroxide that we've added. So first of all, we're going to have to work out how many moles of our carbonic acid we actually have to neutralize. So that's moles per liter. From our concentration, use the volume, which is 140 milliliters, and then convert milliliters into liters. So 1 milliliter is 10 to the minus 3 liters. And that is going to give me what number of moles now? 0.03162 moles of my carbonic acid. And then I am going to need to work out what is going on with my added hydroxide. So I didn't write an equal sign in there, oops. I have my concentration of my hydroxide. I don't actually know from this how many, what volume of hydroxide I've added, but I can work that out because I've got its concentration and I know how many moles that I have to neutralize because I just worked it out. So my volume of my hydroxide then is going to be that 0.03162 moles that are going to have to be neutralized, and then I'm going to use my concentration. So my concentration was in moles per liter 0.3232. So if I put my moles on the bottom, 0.3232 moles of hydroxide for every 1 liter of solution. That is going to give me my volume, and that's going to be in liters. So I'm going to have to make sure I calculate my total volume correctly altogether in liters. So that is going to give me, liters. What have I got? 0.0967265 liters. That will do of hydroxide added. Okay, so now I can work out from that what my total volume is going to be in a second. My total volume then is going to be, let's see, I had 140 milliliters of my acid, so I'm going to have to convert that into liters to make sure that we can match. I might as well leave it in liters at this point. This makes more sense to me than converting the liters to milliliters, right? Because we know volume, sorry, concentration is given in moles per liter. So that would make more sense to me. So that is going to be the volume of our acid that we started with, and then add to that 0.0967265 liters of our hydroxide that we added, and that gives us a total volume of 0.236727 liters. That's plenty of DPs. That's fine. Okay. So now what I need to do is work out my number of, my initial concentration of my bicarbonate before that hydrolysis reaction starts. So I'm working out like what we're starting this reaction with here, which is why I needed the total volume. So my concentration initial, I'm going to say my initial concentration then of my conjugate base, my hydrogen carbonate ion, is going to be 0.031262 moles of HCO3 minus, and then divide that by the total volume, which is where do we get to? 0.236727 liters. So that's going to give me a concentration in moles per liter, which comes out to be 0.132059 moles per liter molarity. So now I can fill out my ice table. So I now have my initial concentration of my hydrogen carbonate anion. That is going to undergo hydrolysis with water to reform the carbonic acid and yield hydroxide, which is what I'm going to be basing my pH off of, essentially. So let's move this over here. Okay, so initial change, equilibrium. So my initial concentration then is going to be, well, I just calculate the 0.132059. This will start at 0, this will start at 0, and then the change will be minus x, as that is ionizing, plus x and plus x. So at this point, it's like any ice table, and then equilibrium then will be 0.132059 minus x, x, and x. So we're going to stuff those equilibrium values into my Kb equation. So Kb is going to be H2CO3 OH minus divided by HCO3 minus. So we probably haven't been given Kb, have we? No, that would be way too easy. So we're going to have to calculate it from Kw equals Ka times Kb. We were given Ka. So Kb is going to be 1 times 10 to the minus 14 divided by whatever we're given for Ka. We're given pKa, so we have to do 10 to the power of minus Ka to get that. Where did I write that down? That's going to be... I don't know what I wrote it down somewhere. So we end up with Kb equaling 3.98 times 10 to the power of minus 11. Can't read my own writing. So that is then what we can stick our Kb expression equal to. So then we can do x times x is x squared. Let's do small x over 0.132059 minus x. And that is going to be equal to, oh, that's gone horribly wrong. Hang on, let's just Control Z. That's going to be equal to our value for Kb. So x squared over 0.132059 minus x. We're going to do the x as small approximation. This is going to be a very small ionization. That's equal to 3.98 times 10 to the power of minus 11. So we're going to rearrange and solve. So x, which again is going to be the concentration of hydroxide, remember, so we can't just directly get pH from that, is going to be the square root of 0.132059 times 3.98 times 10 to the power of minus 11. So take the square root of that, and that will give us our concentration of hydroxide, and that comes out to be 2.293 times 10 to the power of minus 6. So then I can calculate POH from that. So POH is going to be minus log of the concentration of hydroxide. So that is going to equal for pOH 5.64. So we're not done yet, right? So we have to subtract that from pKw. So pH equals pKw minus pOH. That's going to be 14 minus the 5.64. So that is going to give me a value for my pH of 8.36, which sounds about right, because for the equivalence point for titration of a weak acid with a strong base, that pH should be over 7. It should be a basic pH. So that sounds okay to me.